And this session is Universal Android Routing is back with our speaker, Wen Xu.
Hello everyone, thanks for coming to my talk. So I'm Wen Xu from Kingteam. Today I will share with you the universal root solution of Kingteam. First of all, I want to introduce myself. I am a security research intern at Kingteam. Mainly I focus on Android routing and software exploitation, and meanwhile I'm an undergraduate student at Shanghai Jiao Tong University. I'm a big fan of CTF games and I'm the vice captain of Team Oops. So we will participate in the DEF CON CTF final tomorrow and hope us good luck. Here's the roadmap of my talk. So first of all, I will talk about the present situation of Android routing. Then I will show the highlight parts of our work, include an awesome bug we exploited to achieve Android routing on Android devices. And the second part is about the exploitation techniques we used. And at last, I will talk about the future of the Android routing. So let's start. So the question before we do the Android routing, we must make clear that what do we root for? So when it comes to Linux routing, maybe the goal is to get a root shell with the privilege of a root user, but somehow it is meaningless when we are doing Android routing, because if we want a permanent root on Android devices, maybe we should put the SU binary on the system partition, and then if we only have a root shell, then that won't be enough. In fact, we need a kernel arbitrary read and write ability. So, currently many Android devices are protected by many protections or mitigations from these vendors, such like SE Linux or some protections that even you are a root user, you cannot run arbitrary binary files under specific folders, or you cannot remount the system partition, then you cannot put the SU binary under it. So these things are all in the kernel. So if we have a kernel arbitrary read and write ability, then we can take all of them down and achieve our goal. So the second question is that what vulnerabilities we need to do a root on Android devices. So here I list some vulnerabilities in drivers on Android devices. All of them are found by Kingteam members. So we used to use these vulnerabilities in our root tool to root Android devices. But one problem is that these vulnerabilities are all in the is all in the drivers. So maybe in Qualcomm processors or Tegra or something like that. So these are not universal vulnerabilities. In fact, we need a universal applied bug, then we can do a universal root solution. So we want to make a big deal. So we want two things. One thing is that we want to need a universal applied bug in Linux kernel source, not in a specific driver or something like that. And the another thing is that we want to use the universal applied exploitation techniques which can be applied for hundreds of thousands of Android devices, and we do not need to do too much hard code. We need one generic root exploit for all of these Android devices. So last year, remember that there is a universal root tool called Tower Root invented by Jailhouse. So this year, Ping Pong Root is coming back from Kingteam. So let's start. And in fact, I will talk about stories of mine, how I developed this root exploit and what difficulties I met during this process, and how I exchanged ideas with my teammates and finally achieved this goal. So let's start. The first part is about the bug hunting. So once upon a time, so our team leader Wu Xi gave me a zip file and including hundreds of kernel crashes in Linux kernel. So in fact, he got these crash logs from a non-open source syscall fuzzer called Trinity. So everyone could get it online, and but it is based on the desktop Linux. So Wuxi customized it and ported it to the ARM Linux and just executed it on Android devices, and it generated hundreds of crash logs, and he gave them to me, and my task is just to analyze it and find something interesting. So here we are. Amongst these crash logs, I found an interesting one. The kernel has a critical page fault at 200. So that's weird, and you can see that the PC is in the function ping and hash. So let's have a deeper discovery. So you can see that the function ping and hash take sk as a variable, and this argument is the type of struct sock. So in fact, it is a socket object in kernel, and you can see that it is passed into the ping and hash. So it is a ping socket object in the kernel, and the attackers can create such an object in his user program by calling socket and specifying the ICMP protocol. So in fact, the kernel crashes in that function called hlist_new_style, which I marked it with the red underline. And because this function is inline, so if you only take a look in the crash log, you cannot know that where the exact location the crash happens. So let's go into it. And so my first task is to find where this 200 comes. So that's weird. So in fact, when I have a look at this function, and I know where this 200 comes from. So in fact, the value of this predefined const in kernel source list poison 2 is just 200. And then you can see that when we first call the ping and hash and the first call the hlist_new_style, then you can see the previous member of this node n will be set to the list poison 2. It's just the 200. And if we call this function again, then you can go into that function upper, and you can see that I marked the 2. You can see that the local variable pprev is assigned by this previous member of this node n, which is 200, and then immediately there's a dereference on this local variable, and then there's a dereference on 200. And if we not map this value in user space, then the kernel crashes with a critical page fault. Right? So here we got the root cause of this vulnerability, and we should try to find a proof concept of this vulnerability. So how could we make the roads to this ping and hash function? So in fact, it is interesting. So you can see that the ping and hash function is called in function UDP disconnect, but the UDP disconnect is called in INetDgram connect, and with a special SA family specified called AP unspec. You can see that the disconnect in kernel is called as you call connect in the user program. So that's interesting. And here we are very clear about this proof of concept to reproduce this kernel page fault. We just create a socket by specifying the protocol as ICMP and make two connections to it with specifying the SA family as AP unspec. Then we got a crash. So I stuck at this place for a long time because I want to. So a local denial of service is not my goal. I want to achieve the root. So this is not enough. So I stuck at this place, and I want to manipulate the hlist pointers to find something interesting, but I failed at last. So I turned my interest to other crash logs for about 2 or 3 weeks. Then I found that this one is the most hopeful one. So I just turned back to it. and I make some tries. So in fact, this time I map 200-200 in user space, then I make 2 connections, then the kernel won't crash. But I have a good programming habit. I just close all of these sockets before I quit my program. But an interesting thing is that the kernel crashed when I close the socket object, and I go deep into the source. You can see that when I close a file descriptor in user space, then the kernel will call inet release. And then there is somehow like a vtable of this socket object. It is just called skprot, and it is an array of the function pointers. And when I close it, one of the function pointers called close will be invoked. And then the kernel crash. So I realized that it is a typical use-up-free vulnerability maybe there, because that skprot value has been corrupted. And let's see what happened. So, in fact, when I had a second view into the source, and then I found that immediately after each list newsdale, there is a function called which named as sockput. So, if you are familiar with Linux kernel source, you know that there are some function called blah 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 put. Then it's just decrease the reference count of this object. And if the reference count of this object equals 0, and then the kernel will free it, right? So here we are. If we map the 200-200 in user space and avoid the kernel crash, and then make 2 connections, and then the kernel will free it. But we have a downlink file descriptor associated with this pin socket object in the kernel, in the user program, under our control, right? So this is a typical user-free vulnerability in the kernel, and it has a CVE number called CVE 2015-3636. So here we are, we have a user-free vulnerability, and in fact, if we can control the content of the freed vulnerable pin socket object, then we can control the PC register by calling close. So next part, I will talk about the exploitation of this vulnerability. So first of all, when it comes to use-up-free or exploiting a UEF vulnerability, the most critical issue and the annoying problem is the refueling. So we must have the control of the freed vulnerable object. That's critical. So this time, our target is this structure socket object in kernel. And disappointingly, it is allocated in a custom use cache named ping. So let's take a review of slab cache. So basically, slab cache is a kind of storage unit in kernel storing objects of specific type. So in fact, he provides a separation between kernel objects. So these are the difficulties I meet when I'm developing this root exploit. First, the object is allocated by a slab allocator. So the slab allocator provides a separation between kernel objects, so it is not very easy to use another type of kernel objects to override the vulnerable object. It is somehow like the isolated heap in Internet Explorer. So the second thing is that the candidate kernel objects. So we must find a controllable candidate object, kernel object, to do the override, because we cannot directly allocating or deallocating the kernel object. So this is another issue. And the third thing is that we must overcome the multi-threading support of the kernel, because when your attack program is executing, there are hundreds of active tasks running simultaneously scheduled on the core. So they will have impact on the layout of the kernel heap. So that's another problem. And the final problem is that we must control the content of the vulnerable freed object. But we do not have a string in the kernel, right? So that's 4 difficulties I conclude. So my initial plan is to use the kmalloc buffer. So I think kmalloc buffer is somehow the string in Linux kernel. So kmalloc buffer is exists in hundreds of flows in Linux kernel. And in fact, it has several choices on sizes. You cannot specify any kind of choice you like. Just most of them are powers of 2. So you have kmalloc 128 buffer, you have kmalloc 256 buffer, something like that. And how to create it? So here I recommend a choice. There is a kmalloc buffer allocated in process of send message, which is also used in tower root. So basically, in tower root, GHOT use this buffer to override the initialized stack memory. But if the size is large enough, then kernel won't put the buffer on the stack, but instead use kmalloc to allocate an area and put the data into it. And if we use the send message, we can control the size because the size is just the length of the control message you want to transfer via send message, and the content is also controlled by us. So my initial intuitive idea is to use kmalloc buffer to override the vulnerable objects. I just want to spray the vulnerable objects and free all of them, and maybe the slabs storing these vulnerable objects will be recycled by the kernel for future allocation, and I hope that this area will be used to storing the kmalloc buffer later when I spraying the kmalloc buffer. But this plan is out of control and has a really quite low success rate. So I want to improve this. So basically, I was writing my first root exploit targeting this vulnerability on Goldfish, which is an Android emulator. And on this emulator, the size of the vulnerable object, pin socket object, is 512, which is a kmalloc size. So here, I want to say that the slab allocator helps us. So the newly adopted slab allocators try to merge different objects of the same size into one cache instead of the same type. So it just give us an opportunity to use the kmalloc buffer to override the vulnerable objects. So if the size of the vulnerable object is 512, then I can use send message to allocate kmalloc buffers to override it. So I'm excited. I finished the exploit on the emulator, and I told this result to my colleague Liang Chen, and he told me that you should try to test your exploits on some other Android devices, real Android devices, and disappointedly, I found that the size of the pin socket objects varies on different Android devices, and maybe on this Android devices of Samsung, the size of the pin socket object is 576, and another Android devices of Sony, maybe the size of the pin socket object is over 600. So you cannot use the kmalloc 512 buffer to override all of them. And my goal is to achieve a universal generic root exploit for hundreds of Android devices. So that's not the final plan we use. So here's our final plan. The first part of our universal solution is to control the kernel memory. So in fact, I stuck at this place also for a long time, and I like reading academic paper, and there's the academic paper called Return to Dir, and he used FISMAP to bypass kernel protections like SMEP or SMAP. But an idea appeared in my mind that could I use the FISMAP to help exploit use-out-free vulnerabilities in the kernel? So let's take a look at the FISMAP. So FISMAP, also called directly mapped memory, is just a mechanism which directly map the memory in user space into the kernel space for promoting the efficiency of the kernel. So you can take a look at this picture, and in the FISMAP, all of these pages are physically continuous. So here's my idea. I want to use the FISMAP to do the overwriting. Note that the FISMAP is not a kernel object, so it has its own advantage. So how to create a fist map? It is very easy. An attacker just iteratively call mmap, and then mmap of a size of 256 megabytes and fill in the proper payload he wants for the following root exploit. So the fist map will, our payload will grows in a kernel while occupying the freed memory. And we hope that the fist map will use the space once occupied by the vulnerable ping sock objects for his expandation. So here we are. So first thing is that we want to make sure that the fist map can cover the slab caches. So we can take a look at the size of the fist map. And for example, on ARM32, the fist map has a size of 716 megabytes, and it is large enough to cover the slab caches. So here is the first thing. And so my initial plan is to allocate large amounts of vulnerable pin socket objects, and then I free all of them. And I iteratively called mmap and hope that the fist map will make some memory collisions with these freed slab caches, which once stored the vulnerable pin socket object. But in fact, if you try this, the success rate is still not very high. So let's move to the second step. We want reliability. So if we want to achieve a reliable memory collision, we must make some changes. In fact, this time I want to spray the vulnerable pin socket objects in group. So every 5 pin socket objects, which I consider them as the normal ones, I just free them by closing it. Then I allocate 1 vulnerable pin socket object. So every group, 500 normal one and 1 vulnerable one. So why I do this? Because I want to make sure that the pin socket object, the vulnerable pin socket objects are placed everywhere in the kernel space. And then that sharply increase the probability that the fist map and the vulnerable pin socket objects will meet together. And after I achieved the exploits based on this idea, the success rate sharply increased. But in fact, I do not want to throw a dice. I want to definitely know that there are vulnerable pin socket objects already covered by fist map. So here's the third step: create an information leakage. So in fact, we found an info leak. We can call I/O control on that pin socket object in the user program with specifying this timestamps options. Then you can get a D-word value from this pin socket object, and then if once we iterative mmap and fill in our proper payload we need for the root exploit, we also need to fill in some magic value I called. So then when I am do the spraying, in each stage I will call I/O control on these vulnerable objects, and then I will get the return value from this I/O control. And if it just equals to the magic value or correctly reflects the magic value once I filled in, that means this vulnerable object has already been covered by fist map and I got it. So this information leakage also helps improve the reliability of our root solution. So let's make a summary. So first, we spray our pin socket objects in group every 500 normal ones with one vulnerable ones, and we freed all of them. But for normal ones, we just close it, releasing them normally. But for the vulnerable one, we trigger the use-out-free vulnerability. And these objects will be freed and make large free spaces in the kernel, and then we hope they will be used for the growth of the FISMAP with our payload. And then we iteratively call mmap. We do the FISMAP spraying and filling the payload, the addresses we need for the following root exploit, also the magic values I mentioned before. And then at each stage we call IO control on the pin socket objects, that file descriptor we own in user program, and then we check the return value. And if one vulnerable object is already being covered, then the spraying just stops. So in fact, I've presented not just a root exploit targeting this vulnerability, but a generic memory collision model targeting use-out-free vulnerabilities in Linux kernel. So this scheme, this plan overcomes the difficulties I mentioned before, and it is hard to mitigate it because I use the inherent property of Linux kernel, because the FISMAP is just the mechanism of the memory management of Linux kernel, and it always occupies the space in the kernel. And if there is the memory is free, then there's probabilities that this memory will be for the growth of the FISMAP with the data in the user space, right? So it is an excellent plan targeting use-out-free vulnerabilities in Linux kernels. This is the key point I want to mention. So here we are. If we control the content of the freed vulnerable pin socket objects, then we control the PC register, right? So because the skprod, the virtual address of skprod, this so-called arrays of function pointers, is controlled by us, then we can just control the PC register and then return to the shellcode in the user land. So what does shellcode do? So Zhihao told us this again in his tower root. So in fact, the shellcode needs to do two things. First, it should leak the kernel stack address. And when we got the kernel stack address, then we got the address of the thread info. And if we got the address of the thread info, then we can patch, override the ADDR limit of the current thread of our representing our attack program. Override this ADDR limit to 0, and we got the kernel arbitrary read and write ability through pipe. So here we are. So I've presented the root exploit for the 32-bit Android devices already, but back to our goal. We want to achieve the universal root solution, and there are 64-bit Android devices on market now. So what about 64-bit Android devices? Does the bug exist? Yes. So does the list poison 2 also have the value of 200? So this is a serious problem, because when our team want to exploit the 64-bit devices, I just propose a guess that maybe the list pointing to cannot be mapped on 64-bit Android devices. But surprisingly, this time not disappointedly, its value is also 200, and that can be mapped. And could I achieve the memory collision between the FISMAP and the vulnerable objects? And the answer is yes, after we doing some experiments in practical. So in fact, although the 64-bit Android devices has a larger virtual address space, but the memory of the RAM, the size of the RAM is limited, and the collision will finally happen on 64-bit Android devices also. And then the last issue is that could we just simply return to the shellcode played in the user space, and for some Samsung devices like S6 or S6 Edge, you cannot do that because PXN is applied. So we have to. So the first thing up in my mind is, could I just return to the FISMAP? We can place our shellcode in the user space and change the property of the memory to executable, and then they will be mapped through FISMAP into the kernel space, and then we can just return to the kernel space. But disappointingly, again, the FISMAP is not executable on ARM devices, on Android devices. So we have to do the ROP, kernel ROP. So the kernel ROP have two stages. The first stage is to construct a ROP chain and leak the kernel stack address. And the second ROP chain is to just override the ADDR limit to 0. But a pity is that we have to do some hard code here. That is because if we haven't achieved the kernel arbitrary read and write ability, we cannot search the kernel memory and find the gadgets we want. So we have to dump the ROM and put it into IDA and find the gadgets, and we have to hard code for every types of ROMs. So here is a thing which is not very universal in this universal solution. So in fact, my teammates. So at first, I finished an ROP chain and compromising the Samsung S5, and then I'm turned to some other work, and my teammate QB, he continues my work and write more ROP chains for different Android devices, and they say that disappointingly, my kind of attack cannot work very well and have certain failure rate on some devices. So in fact, QB rewrite my ROP chain. In fact, he preferred JOP instead of ROP. The reason is that if we use ROP in kernel, then we couldn't avoid the stack pivoting, but the kernel will schedule every task, and if the stack value is corrupted, then the kernel will be crashed and bring some unexpected results. So we should use JOP. We just jump, and finally achieve our goal. We cannot corrupt the stack value. So here are some tips. So basically, you should make full use of the value of the registers when you invoking that corrupted function pointers. At the beginning of the ROP chain, you should make use of these values of the current values of the registers. And another thing that if you are in the exploiting 64-bit Android devices, the high 32-bit of a virtual address in the kernel space remain the same. So if you find a gadget that just read or write the low 32-bit of the virtual address, of a kernel virtual address, then that will be helpful. And in fact, we found some God gadgets in some ROMs, and we only use this one gadget, and we can achieve 2 steps. We can combine the 2-step leakage and overwriting into one, and then maybe left to you guys to find it. So here we are with the help of my teammates, James Fong and QB, and with the vulnerability from Wu Shi, finally we achieve a universal root solution, and we can leverage it to root most popular Android devices on market. By the way, the version should be higher than 4.3. And also, we have the first 64-bit Android root case in the world, as we aware, and we just released our root solution targeting Samsung Galaxy S6 and S6 Edge on XDA forums, and I heard from my colleagues that there are already over 300,000 people downloading it and root their Android devices. And here's a piece of demo. So here is a Galaxy S6, and you can see that we click it, our root solution, and it will first install the Super SU, and then the Super SU is installed. Okay, but the prompt says that that there is no SU binary on your system partition, so the device hasn't been rooted. So we just run our root exploit, pack it in an Android application, and then our root exploit is finished, and we reboot the device. And wait a minute. You can see the logo. It is a Galaxy S6. And then the phone is booted. And then we just open an application. We open an application which needs the super user privilege, and you can see that the Super SU prompt and say that would you like to give the root privilege to that application, and that means we achieve a permanent root on these Android devices. And And in fact, based on the research of James Fong, actually we root the Samsung devices without corrupting the warranty bits. So, yeah. So, but the details of that are not included in my talk. So finally, I will talk about the future of Android rooting. So I think 64 Android devices could be more secure. Yes. So the first thing is that, when I reported this bug to the Linux community, some of the guys complaining that why this list pointer 2, the value of list pointer 2 on Android devices is set as 200 for 64 Android devices. So that's not an intelligent choice, I think, because on the desktop Linux PC, I mean, in every distribution of Linux PC on desktop, the value of list pointer 2 is that value, that followed with 12 O's. So, the 64-bit processors currently only use 48-bit for addressing, and this address cannot be mapped definitely. And if I cannot map this list pointer 2, then the kernel will crash, and I cannot arrive at the sock port, that freed location. So another thing that we can prevent the memory collision with FISMAP, maybe we can make some separation between the FISMAP, because these FISMAP are containing the data from the user space for promoting the efficiency. We can separate them from the data in the kernel, So that's another choice. And the second thing is about maybe we can employ the KASLR, which is not employed in current Android devices. Maybe. Yeah. So I think the days become harder for the Linux kernel owners, but when there is a protections appearing, then we may try harder and have some countermeasures to attack against them and bypass them, and then we can improve the community to make their improve the security of like Linux to make it more secure and have a more strong security support. Oh, at last, I want to mention that in this talk, 3 ponies nominations were leveraged. One is about Wu Xi for the lifetime achievement, and he just gives didn't stop giving the bugs to the other members of King Team and support King Team go ahead. And another thing is that about our ping pong root, the universal root solutions is selected as the nominees of privilege escalation, and I also used a basic result, an important result from return to dir, which is selected as the nominees of most innovative research, but disappointingly, all of these 3 fail at last. So, yeah. So, hope us good luck next year. Here's the acknowledgement. So, thanks to Wu Xi, James Fang, and Liu Xi, also known as QB, for their contributions to our root product. Yeah, and thanks to Liangchen, Slipper, and Peter from King Team for their inspirations on me. And the pictures comes from Google. So, thank you all, and questions are welcome. Thank you.